Okay, everyone. So we are going to look at a question 3, which is a module 3 question from the June 2017 paper, right? So this question reads as follows. They're telling us that KClO3 undergoes disproportionation when heated to just above its melting point to produce KCl and KClO4. And they're asking us to define the term disproportionation. And I've written out that for you guys here what the answer would be. It would be that disproportionation refers to a redox reaction in which the same element is both reduced and oxidized, right? So that's for 1 mark. We'd be good with that. So then we move down here now, and they're asking us to write the balanced equation for the reaction above, and hence deduce the oxidation number of chlorine in the KClO3 that gets formed, that we start with actually, and then the KClO4 that gets formed as a result of that decomposition or disproportionation, right? Okay, so here we have our KClO3. We're going to have 4 moles of KClO3. And when we heat that above its melting point, we get this KCl solid, and we get the 3 moles of KClO4, right? So that's our balance equation that we would be able to come up with for that reaction there. And then now, if we look at our KClO3, we see that in this initial case, our K will have an oxidation number of 1. And then, of course, oxygen is always -2 here. So this would be 3 times -2. So what remains is that the chlorine will be in a +5 state here. And then over here in KClO4, we do a similar analysis where the K is +1, the oxygen is -2, right? So when we sum all of this together, we should get 0 since there's no charge on this compound. And so what remains then is that the chlorine would be +7, right? So we can see that in the one case where we go from KClO3 to KClO4, that this chlorine is going from +5, right, to +7. So there's an increase in oxidation number in that case. And then, of course, here, we would have an oxidation number of -1, right? And so we'd be going from +5 to -1. And so in that case, there would be a reduction, right? So we see that simultaneously chlorine is being reduced and it's also being oxidized, okay? So those are the key takeaway for part 2. All right, so moving along to part B, they're asking us to explain the trend in volatility of the halogens as the group is descended. So as we go down the group, what happens to the volatility, right? So as we go down the group 7, what we will see is that the halogens get larger, right? And the number of electrons actually increase. And as a result, this makes the van der Waals forces of attraction between the molecules stronger. And as a result of that, it takes way more energy to break the intermolecular forces as we go down the group, right? Hence, the volatility of the halogens decreases as the group is descended, right? And it's worth noting that if something is becoming less volatile, and that's what's happening as we descend the group, it means that the boiling point is getting higher, right? So that's what's happening as we go down the group. We're becoming less volatile. The boiling point is getting higher because the molecules, the halogen molecules are larger and there are stronger van der Waals forces at play there. And also you might remember that there's a change of state, right? As we go down the group from gas to liquid to eventually iodine being a solid. And certainly a solid is less volatile than a gas would be, okay? So just keep that in mind. And that's what we would put here for our 3 marks, right? So moving right along to part C. Part C is saying that Mx is the formula of a salt of the halogen with a relative atomic mass 80. So the halogen that has a relative atomic mass of 80 is actually bromine, right? So we can go check our periodic table, look in group 7 and see which halogen has a relative atomic mass of 80, and we'll come out with bromine. So I just put bromine here, and bromine is actually what our X is, right? So this is technically a MBr compound, right? So that's what we have here. We have a MBr compound at play here that the student is then going to be testing, right? So the first test that the student did was to warm this MBr compound with concentrated sulfuric acid, right? And we know that the concentrated sulfuric acid is a powerful oxidizing agent. We know that the bromide ion is an excellent reducing agent. So we'll have a redox reaction taking place here as well. And what the student will observe, right, is that there will be this bromine gas given off, right? Because this bromide ion is then going to get oxidized by this concentrated sulfuric acid to bromine gas, right? And so we will see that there's that reddish brown color that's characteristic of a bromine gas being evolved, right? What else is going to happen is that there's going to be a choking acidic smell that corresponds to this sulfuric acid, the sulfur in it in particular, right? That's going to get reduced to SO2 gas. And so we'll smell that choking acidic smell, which corresponds to the reduction of the sulfur from the +6 oxidation state here to +4 where it's in sulfur dioxide, right? So we would know that that's what's going to happen in this case based on our knowledge as to how halides react with sulfuric acid. Okay, so moving right along to the second test, we're adding, or the student is going to be adding silver nitrate to our MBr, aqueous MBr, and then the student is going to follow that up with concentrated aqueous ammonia, right? So what would we observe in that case? Well, essentially what's happening is that when the aqueous MBr reacts with the silver nitrate, right, what's gonna get formed is AgBr, right? So we're gonna form that AgBr precipitate. Let me just add that in here. So actually what this cream precipitate that we're seeing is actually from AgBr forming, right? AgBr solid when upon the addition of this AgNO3. And so that's an insoluble precipitate that we're gonna get. But when the student follows that up with the concentrated aqueous ammonia, what they'll see is that that cream precipitate is then dissolved away in that concentrated ammonia solution. And so they'll just see that that precipitate goes away, it dissolves, right? So that's what would be observed in the second case. And then now if we come down here in the third case, what's gonna happen is that the student is gonna be passing chlorine gas through the aqueous MBr mixture. Again, the X is Br. So what's happening here, right, is that chlorine gas is essentially reacting with MBr, where M is our metal, of course, right? So in this particular case, we know that chlorine is above bromine in the group. So chlorine is a better oxidizing agent than bromine. So the chlorine will come in, right, and kick out this Br and take its place, right? And so what's going to end up being formed then is effectively we will have MCl forming, right? And then the bromine, this bromine is gonna get oxidized now to Br2 gas, or aqueous in this case, right? And so that's what we will see. We'll see a reddish brown color that corresponds to the bromide ion being oxidized by this powerful oxidizing agent Cl2 to then become Br2, right? So we're going from Br minus to Br2, and so we'll end up seeing a reddish brown color that corresponds to Br2 being formed, okay? So that's what we would see there. And then if we continue on down to part D, let's clear that. We continue on down to part D. They're asking us to write an ionic equation to show the oxidizing nature of sulfuric acid in test C, part I. So remember in this particular test, what was happening is that this warm concentrated sulfuric acid was acting as an oxidizing agent, right? And it was able to oxidize the halide ion, so the bromide ion, right? It was able to, first of all, what happens is it would react with the halide ion would react with the sulfuric acid to form HBr gas and HSO4 minus ion, right? And then afterwards, now, because the bromide ion or the halide ion is a very strong reducing agent, and we're coupling that with a strong oxidizing agent, what's going to happen is that this halide ion is going to reduce the sulfur even further. And so we're going to end up getting the halide ion itself is going to end up being oxidized to Br2 gas. And then the sulfur is going to get reduced from that +6 state to the +4 state where we have the sulfur dioxide gas. And of course, there's some water as well, right? So the oxidizing nature of the sulfuric acid here is that it is in effect oxidizing the halide ion, right, from Br minus to Br2 gas, where it's in that zero oxidation state. So that's being oxidized, right? So let me just have an arrow here that shows us that this is an oxidation process that's being oxidized by the concentrated the warm concentrated sulfuric acid. And then by that same token, then the halide ion, the bromide ion, is acting as a powerful reducing agent, and it's reducing this sulfur that's here from +6 to over here in sulfur dioxide, where it's in a +4 state, right? So this, let me put that in a different color and just show you that this process from here to here is a reduction. Right, so that's how those two things are coupling together. Again, the sulfuric acid is a strong oxidizing agent that oxidizes the bromide ion to the Br2 gas, and we're going to see that reddish brown color as we did up here. And at the same time, the sulfuric acid is being reduced, right, from the +6 S state, sulfur state, to SO2 gas, which is reddish brown. So we'll see the reddish brown, well, the choking acidic smell is what corresponds to the sulfur dioxide. So we'll have a choking acidic smell that's permeating the environment, and that will be indicative of the sulfur dioxide being formed, okay? So that's this question from 2017, question 3 in a nutshell. Hope this was helpful for you. Drop a comment and let me know if it was, okay?